In this lecture, we're going to take a brief look at transformers. Not these transformers, but transformers that are even more fascinating, which are feed-forward networks that have recently been proposed in 2017, and that even though they are feed-forward, they seem to be better at dealing with sequential data than even recurrent networks. And being feed-forward has a big advantage because it allows training in parallel, whereas with recurrent networks that is difficult. And the secret of the success of transformers is in the attention mechanism. So I'm going to start by talking about what attention is in artificial neural networks. Then I'm going to present the transformer model, one model for transformers, and we're going to look at that in more detail. So we're going to implement a transformer model to translate Portuguese sentences to English sentences. Now this is unlike the most examples that I use, which are toy examples thought to be designed to be simple. This is actually a more realistic example, even though the model is simplified, so it doesn't take too long to train. So I'm going to take advantage of that to show you some tricks for using carriage and some more advanced techniques. However, I must note that the details that we're going to cover are not required for evaluation. So you don't need to use this kind of sophisticated techniques for the assignment or know this for the exams or the tests. So this is to help understand what attention and transformers are, and also to give you a preview, a kind of a brief introduction to some more realistic approaches to deep learning and what you can implement with TensorFlow and carriage. Okay, so let's start with attention. The idea is that instead of our network just looking at the whole data that we are presenting at the same time, we want the network to do something more similar to what we do ourselves. We are receiving a constant stream of sensorial data, but we focus our attention on specific elements that are more relevant at that each particular situation. So we are not paying equal attention to everything that is coming in through our senses. And the motivation for this was initially the difficulties with encoder-decoder recurrent networks. So imagine that you are creating an encoder-decoder network to translate between English and Chinese, and the technique here is to use a recurrent network here that will convert the sequence of words into a fixed length representation, and this one will then feed into the decoder, and the decoder will use each symbol generated along with this context vector to decide what the next symbol is. And the problem is that even though this works, it has some difficulties learning long-term dependencies. So we saw last week how several solutions like using skip connections and things like that, but one proposal for this was to use attention. So the idea is, initial idea was that instead of generating a fixed context vector, the context vector could be dynamic, and the network learned to create the context vector by looking at the different states on the encoder, sorry. So this would be the encoder. It's a bidirectional network, and it's taking in for example, the words in English, and this layer here learns the different weights, the different parameters, to give different weights to different states of the decoder. And now this is going to be fed into the outcoder, and these parameters are different for different timestamps too. So we can have a dynamic context created here, and this was called an attention layer because it's deciding which parts of the encoder are more important and which are less important for each particular symbol that we're going to output here. So this was called additive layer because it's adding all of these. There are different kinds of attention mechanisms other than additive attention. We're going to see one particular one, which is the one proposed with the transformer architecture, which is this scaled dot product attention. But before I go into that, I just want to say that this approach of using attention mechanisms worked really well. So it improved a lot the way the recurrent networks could solve this kind of problem. And in fact, it worked so well that in 2007 it was shown that we could do 2017 it was shown we could do away with the recurrent networks and actually use a feed-forward network with attention, and that would solve the problem. And this is much better because with recurrent networks we cannot parallelize training so well as we do with feed-forward networks. So feed-forward networks scale more, are faster to train, are easier to train, and so there are a lot of advantages here. And the idea is now to generate, we have this feed-forward network that receives as input the input sequence. For example, in this case, it could be a sentence in English, and then it would receive as input also what the beginning of the output sequence. And from that, it would predict what the next token, what the next word would be. And it would we would feed again this data, now with the additional word, and keep repeating that until it generates all the sequence. Okay, so the attention mechanism used in this transformer architecture that we're going to look into more detail is the scale dot product attention, and we can think of this attention to be to modify some set of values that are going to be multiplied by this softmax vector. That the softmax, remember, outputs vectors between 0 and 1, and a normalized vector that is everything adds up to 1. So we can use this softmax to determine which parts of this vector are more important and which are less important. And what determines this is the product, the dot product, the inner product of these two vectors here, which are actually this is the dot product, so this would give you a matrix, but then this tells you the alignment, so to speak, or the correspondence between what is called the query and the keys. So this the keys would be for example, the input here, the words. The query could be what is being generated, but this is merely conceptual because, as we're going to see in the model, we can even use this attention layer as a self-attention, so looking at always the same vector in all the three inputs. It also works like that, but basically we are looking at the correspondence between these vectors, and that will determine how important, more or less important, this other vector here is. And the network will then learn to create the appropriate representations of these vectors so that at the layers, at the attention layers, this will help focus on the important features. There are other attention mechanisms, but we're going to look at this one, which is the one implemented in this transformer architecture, and it's called scaled dot product attention because we are scaling this by the square root of the dimensions of these vectors here. So query and keys have the same dimension, and we divide by the square root of this dimension so that we retain these products more or less in the same scale, the same variance, and so on. Okay, so let's see how this works. In fact, in this transformer, the authors propose a multi-head attention layer. This is the attention, the scaled dot product attention. So we're going to multiply these two vectors, the query and the keys. We're going to scale this by as a function of the length of this vector, so this scaling factor here. And then we're going to use a mask, we're going to see why, because we have sequences that have a fixed maximum length. That's the size that our network can input, but we cannot, we may have sequences that do not cover everything. So we may need a mask to ignore some parts that don't have words. For example, if we have a sentence that has less words than the maximum allowed. Then we use softmax and we multiply by the values to determine which are more important and less important here. The multi-head attention is merely an extension of this. We are going to project this with linear layers into several blocks. We're going to use for each block the scaled dot product attention, so this block here for each head in this multi-head attention, and then we're going to concatenate and project again to the same dimension. So this would be dense layers doing the resizing and the projection of this data. And this is the number of heads that we're going to use. The reason for this is that when we have independent dot product attention layers, these independent projections will help focus on different aspects in parallel, and this helps learn, for example, relations at different scales or different types of relations easier. So this is the transformer model. We have an architecture that is also an encoder and a decoder, but this is not a recurrent network. This is a feed forward. And what we do is we input here the input for the translation, for example. So the idea is that we're going to receive one sequence and output generate a sequence. For example, in the particular example we're going to look at, we're going to receive a sentence in Portuguese and output a sentence in English. So here in the encoder, we input the input sequence, and in the decoder, we input the sequence that has been generated so far. So in the beginning, it's just a start token to indicate that we are going to start generating the output sequence, and here we input the whole input sequence. So the encoder has a number of blocks like this that have a self-attention layer. So this is the multi-head attention layer, but it's applied to the input vector. So you can imagine this being applied to the same vector on the three arguments. This is called self-attention because now it's learning to look at the sequence of words itself and determine from that sequence which are the more important parts. And now we're going to put this into this feed-forward block, and this includes layer normalization. Layer normalization is similar to batch normalization that we saw, but it normalizes for each layer, for each example. It normalizes all the values in each example. And we also have these residual connections. We're going to see how we implement them, but basically what we are learning at this layer is to output the sum of the input and whatever was learned here. So these are residual blocks that we saw some lectures ago. But basically this is one unit for the encoder, and it will have n of them. We can stack several of these, and then the output from this last layer will feed into the attention layer of the decoder. So here we have, in the decoder, we have a self-attention layer. Again, we input the sequence that has been produced so far. We have this self-attention layer, and then this is fed as the values into this multi-head attention layer here that will then determine which parts are more important or less important in the sequence we are generating, depending on the input sequence. So it joins the output of the decoder here in the encoder, and then we do again a feed-forward layer. We're going to look at this. This is actually a stack of two layers with rectified linear units, and the residual layer and normalization, and then a dense layer here and the softmax output. This softmax output has as many output elements as the number of different tokens that can be generated, and it predicts what the next token will be given the sequence produced so far and the input sequence that we feed into the layer. So when we want to generate new sequences, we put, for example, a Portuguese sentence here, we put the start token here, and this predicts the first English word. Now we put the start token and the first English word here and the Portuguese sentence here, and this predicts the second word, and we keep doing this until the model outputs the end token, indicating that it reached the end of the translation. So this is how the model works. It's not a recurrent network. We are just feeding in different inputs, but it can be used in the same way to generate sequences. Okay, so let's see how we can implement this. I think I'm going to have to go a bit fast on the implementation, but you can experiment this for yourself. And in any case, I'm following this tutorial that you have on the TensorFlow documentation. So if you want to do this tutorial, you can follow it, although it doesn't have much explanation, but you can follow the code and look at it with more time if you want. So what we're going to need is the data set. We're going to create a transformer to translate Portuguese to English. So we need a data set with Portuguese and English sentences matched together to train our model. And we're also going to need a tokenizer. This tokenizing is used in natural language processing because we cannot really put in a text sentence here into our model. We need numbers for the neural network. So what the tokenizer does is it creates a dictionary of the words that you have in a language or in a data sample, and it converts those words into numbers. So we have word number 32, word number 54, and so on. And if you present a sentence to the tokenizer, it will give you a vector with the numbers identifying each particular word in that vector. So you're going to need that as the starting point for our training for the handling the sentences. For this, you're going to need these two libraries. So if you only have Python in Anaconda and you have everything in the base environment, you probably only need to use pip to install these libraries. If you have different environments, then remember to install this in the same environment where you are using TensorFlow. So this allows you to use the data sets that you have available for tutorials in TensorFlow, and this is the module for processing text. Now we can import the libraries that we need. We're going to load this data set for the translation from Portuguese to English. So the first time you do this, you load the data set, it's going to download the data set into your hard drive. It's about 120 megabytes, something like that. But if you run this again and you already have it in cache, it will just load the data. We also need a tokenizer specifically for this translation from Portuguese and English. So you're going to load this particular model that you can get here from this site. So you can use the utilities Keras to get the model and then load the model here. So this is what we're going to need to convert words into numeric vectors automatically, and this is the data set that we're going to use to train our model. Okay, so this is the setup. Now let's start by creating a pipeline for our data. So this is more sophisticated than what we saw so far, but if you use this dataset class from TensorFlow and these data sets that you are using in the TensorFlow data sets, they output these data set classes. and you can specify how the data will be processed. So in this case, we're going to create pairs of tokenized tensors for the different sentences. So we take a sentence in Portuguese from our data set. We use the Portuguese tokenizer to convert that sentence into a tensor of numbers, into a vector of numbers. And then we use the two tensor to create a tensor with the correct dimensions, padded at 0 where there are no words, and so on. So we are going to create these tensors in this function. So this function will use the tokenizer and convert the sentences in the data set to tensors with integers indicating the identifier of each word. And now we're going to create the data set for the examples by chaining these different methods of the dataset class. So these train examples are the dataset are elements of the dataset class, and here the batches are also these dataset objects. But we are going to chain all of these method calls. So cache without a file name tells TensorFlow to cache everything in memory. This is the size of the shuffle buffer, because if you use a shuffle buffer with the same size as the dataset, then everything will be shuffled. If you use a smaller size, the TensorFlow will cache this smaller buffer and take, for example, the first 20,000 elements from our data. And then when you create a batch, it will sample at random from those 20,000 and insert at random others from the complete data set. So basically, this is not completely shuffled, but it allows you to control how much memory you're using for shuffling the examples. This is the size of the batch. This is the map allows you to automate using a function to transform each example into something that you want to use. So in this case, our data set is in strings, in text. We are going to use the tokenizer to create the numeric vectors. And you can also automate using this in parallel. So if you have several CPUs, cores, and so on, TensorFlow can do this in the CPU in parallel while it's training the previous batch. So you have this prefetch of batches that allows TensorFlow to optimize the load on your computer by prefetching some batches while others are still training. So all of this can be optimized using this dataset class. This is just an example. If you're interested in this, you can look at the documentation and more examples. But this is a more advanced object that we didn't use so far, but I just wanted to call your attention to this, because when you're dealing with more demanding problems, it can be useful to work with these objects. Okay, so another thing that we need to do is to add positional information to the words, because we are not using a recurrent network. We are using a feed-forward network and looking at all the words at once. So we want to have some indication of how close together the words are in the sentence or further apart, and so on. One way of doing positional encoder is to use this formula here, which is to create a vector of this I is the size of the representation that we are is the position along the vector for this number of elements. This is the depth of the model. For example, we are using vectors of 128 numbers to represent the words. This would be 128 here. And we are using sign for the even indices in our vector and cosine for the odd indices. And this is the position in the sentence. So these strange formulas give something that looks like this. So as we go along the position, we have these vectors that we see here in the vertical, and the interesting property here is that if you look at vectors in nearby positions, they are very similar. But if as we go apart, they start becoming different because for the same index the value changes a lot, and this gives us basically an encoding that we can use to specify the position of the words in the sentence. And now we can add this to the embedding of the word, that is the vector representation of each word, so that words will be similar if they have similar meaning and they are close together in the sentence. If they are very far apart in the sentence, then the vectors will be more different because we are adding this positional encoding. We're going to see where we're going to add this, but let's just put this out of the way. This is basically the function for the positional encoding to create these angles, the expression there, and then to use the sine and cosine for the even indices and the odd indexes of the vectors representing the words. So basically this gives us these values for helping encode the positional information. Now we're going to also need masks because when we are training the model and trying to predict and predict the input sentence, we have a vector with a sequence of words, but we have a maximum length for that vector that will not always be used because not all sentences will have the maximum number of words. So we need to have this mask that looks at the zeros where there are no words and basically creates a mask indicating with the value 1 the positions where there are no words in the sentence. And we also need a look ahead mask because when we are training the model or trying to predict, where do I have the model? Here. We have to present the sequence that has been generated so far. So if we have the target sequence, and we're going to see this in training, we need to hide the next token so that the model does not learn to output a prediction by looking at the token that should appear next. So we need this mask to hide that next token and get the prediction only from the previous ones. So basically what this does is uses this band part method to create this diagonal. So for the first iteration we're going to look at the first token and hide the others. The second one we look at the first 2 tokens and hide the others, and so on. But these are just auxiliary functions so that we can create these masks and hide the parts that we don't want the model to look into on the sequences. Okay, so now this is actually the function for the dot product attention. We are going to multiply these 2 matrices here. This is the dot product part, and then we're going to rescale this by the shape of the depth of this part of the model, that is the length of the individual vectors in these matrices. So this is the last dimension, and we're going to divide by the square root of that depth. And now we can check if we need to mask something, because before we pass into the softmax, we need to see if there are parts of the sequence we need to ignore. For example, parts that don't have words, or parts that have words that we don't want the model to look at because they are the next words coming up. So wherever there is the mask, if the mask is 1, we're going to put a very large negative number. So this is minus 1 million, minus 1 billion here in the logits, so that when we do the softmax, this effectively comes out as 0. So we are telling the attention layer to ignore everything that is under the mask and focus only on what is outside the mask. So we can now create a layer for multi-head attention. Note that you don't need to learn how to create layers here. You can do for the assignments like we did before, using global variables and so on. But this is just to show you how you can do it if you want in your models. We can subclass the base layer class from Keras. And what we need are two methods. We need the constructor here, the init method, that will create the layers that we need. So in the case of the multi-head attention layer, we're going to need these dense layers for the projections of the different inputs, the queries, the keys, and the values. We also need the dense layer for the output, and the dimension here will be the depth of the model. Now we also need to split these outputs into the different heads. So we're going to reshape this. We need to make sure that the total dimension of these vectors, the depth of the model, is a multiple of the number of heads. Otherwise, this doesn't work. We cannot split through the different heads. But to split, we just reshape this and add another dimension. So basically, what we're doing here is we are projecting, for example, into 128 values for the vector, and then splitting this, for example, between 8 heads. So we add a new dimension to the matrix. This transpose is just to adjust the position of the different dimensions. And so we split this into the 8 different heads. And now we also need to create this call method. This is what is called when the layer is actually used for a computation. So we're going to pass the inputs through the dense layers that we created here, the dense layers for the different inputs. These are linear outputs on these layers. Then we're going to split into the different heads, and we're going to do this dot product over for the different heads. So this does the scale dot product for the different heads in one operation. And now we're going to adjust the dimensions again because of the order of the heads and the vectors and the batch. And we're going to pass the concatenation of everything into the final dense layer, so that we have this the output for the multi-head attention layer. So this we can create as a Keras layer, and now we use it as if it was just a layer in our model. Now we're going to need this other stack of feed-forward layers that we saw here in the model. So this blue rectangle here, this is a stack of 2 dense layers, with the first one having a potentially larger size. So this is DFF, maybe larger than the in general the model keeps the dimension of the vectors, has a ReLU activation, and then we project again into the size of the depth that we're using. So we can use, for example, in most cases the vectors are represented with 128 values. This would be the depth of the model. But we can have on these layers, for example, an expansion to 512 and then back again to 128. So this gives us more power to transform the data on these layers here and do a nonlinear transformation here on the ReLU, and then do a linear projection again to the original dimension. So this, we can create this auxiliary function so that when we create a block for the encoder, note here, going back to the model, that we have these encoder blocks contain the self-attention, the feed-forward, and the normalization, and so on, but they can be repeated n times. So we can stack these blocks for a deeper model. So we're going to create one of these encoder blocks as a Keras layer here. And this starts with the multi-head attention layer that we created previously. Then this point-wise feed-forward network that does the expansion and the projection again. We have the layer normalization layers and the dropout here. So this initialization simply calls the initializer for the base class and then creates the layers that we need. And the call method actually puts everything together. So we receive this X vector. So this is the output from the previous block or the input into the encoder block. And we create this self-attention. We pass through this self-attention layer where the keys, the query, and the values are all the same vector. We also have a mask because we may need to mask the parts of the vector that do not correspond to any words. So then we use this dropout. We do layer normalization for this tensor here. And note that here we are doing a residual block. So this layer for the normalization will receive as input not just the output of the previous operation, but also the input that we have here. So this means that this part is learning the difference between the input and what we want to come out of this whole block. And this is, if you remember what we saw, what we do in a residual layer or a residual block. We are learning the residual, the difference between the input and the desired output. Now we pass through this point-wise feed-forward network, so that stack that does the expansion and contraction again, and dropout, layer normalization, and again we have a residual block here connecting this output to this output here. So note that we are summing this part and we return this output. So basically this is one of these blocks here that you can see, which has these residual connections, the feed forward, the self-attention, and the normalization there. Now we're going to do the same thing for the decoder blocks. We have the initialization, we create the two multi-head attention layers that we need, the normalization layers and the dropout, and this feed-forward network. And now what we do is we have this self-attention, but we are now inputting the sequence that has been generated so far. So this look-ahead mask will cover everything that has not yet been generated. Then we have the dropout, the layer normalization, doing the residual, making this a residual block here because we are adding the input. Then we have another multi-head attention, but this one now includes the output from the encoder. So the output from the encoder enters here at the second attention layer. As you see in the architecture, we have this first self-attention layer here, and then we have another attention layer that is including the output of the encoder along with the input to the decoder here. So this is how we can create this into a decoder layer, and then we include the feed-forward network, the dropout, the last normalization. Again, we are using residual blocks here. Note how we are adding the output at the end of the block to the input into the block, in this case the output here. So this creates those residual connections by making what is between these layers learn the difference between the input and the output. And this improves training when you have very deep models. And now we do the final layer normalization, residual, and so on, and we output the output here. In this case, the layer also outputs the weights of the attention layers. This is not necessary for what we are doing here because I'm only following the tutorial until we have results and I can show you the translation. But if you want, the tutorial also gives you the visualization of this weight layer. So I leave this like this if you want to get the weights to visualize them later. Okay, so now we can bring together those encoder blocks and create the encoder part of the model. So now we're going to create this whole part here, which includes the input and the embedding and the positional encoding and a number of blocks of these encoder layers. So to do this, we're going to need first to add an embedder here. So this embedding layer is a layer that Keras provides that basically maps between the integer identifiers of each word. So remember that we are encoding the sentence into a vector of integers, indicating that the sentence starts with word number 32 and then word number 413 and so on. But now we are going to convert this into an embedding which has this depth, for example, 128 values, which are float values. And what this layer does is a mapping between each integer and a different vector that is going to be learned. So the embedding layer will be trained along with the training of the whole model to find the best mapping between the different identifiers of the words into vectors that are useful for this particular problem. So probably words that have similar meanings will tend to be in similar vectors. Words that are very different will be embedded into different vectors. But the idea is to take all of these numbers that can be many thousands. This is the size of the vocabulary for example, the Portuguese sentences, into float vectors that have a fixed size. For example, 128 elements. And this will be learned during training how to map this properly. So this would be one layer that we have to convert each array of integers describing a sentence into a matrix that has one vector for each word. Then we're going to compute the positional encoding vectors for this, and because we're going to add the positional encoding to the embedding here. This makes the words that are close together more similar than words that are far apart in the sentence. And so this is how the encoder will work. It will create a number of encoder layers, those blocks that have here. The number is defined by this parameter. And then when we call the encoder, it will create the embedding of the token vector that we receive. It will multiply this, it will rescale this by the size, the depth of the model, because this is basically so that when we add the encoding, the positional encoding, we can calibrate how much weight the embedding has and the positional encoding have, because we cannot put too much on the positional encoding or too much on the embedding. So basically the embedding is scaled by the square root of the depth, the number of values that we have in the vector, and then we add the positional encoding for the different positions along the sentence. So now we have a dropout layer for these initial vectors, and then the encoder blocks, the encoder layers, which have this number of layers here that will be stacked together, and then the output from that will be the output of the encoder model, of the part of the model that does the encoder. We do the same for the decoder. So the decoder also needs to have embedding, also needs to have the positional encoding. So this part is the same. Now we have just the difference is that we have this stack of decoder blocks that are stacked together, and each one is receiving the output from the encoder. So we are creating in the encoder, we are creating this part by stacking a series of encoder blocks, and in the decoder we are stacking a series of decoder blocks before going to the softmax there at the end. So this would be the the decoder, which ends here after the so we put the softmax on the model, sorry, but here we are stacking the different decoder blocks, and we are creating a dictionary with the activation, the weights of the attention, the multi-head attention layers, because if we want to visualize them later, the decoder block also returns this dictionary with all the weights of the different decoder layers. Okay, so now we can create the model. We create this, use this tokenizer for converting the sentences into the vectors of, oh, sorry, I'm confusing with the other one. With the tokenizer is called here is actually the encoder. The encoder model, the encoder layer that we created here. So this will receive the vectors of the sentences, where each word is identified as an integer. We'll compute the embedding, pass through those blocks of encoding, and produce the output from the encoder. Then we have the decoder, also the decoder part of our model that will receive the input from the encoder and from the sequence that has been generated so far. And then we have the final layer, which is a dense layer with this target, the size of the vocabulary for the target sentences. So in this case would be English, because it needs to output a prediction of what the next word will be. So we have, when we call the model, the transformer model, it passes the input through the encoder part using this padding mask that indicates where the input vector has no words. So we have a maximum size for the input vector, but some sentences may not have as many words as the maximum, so those parts will be masked. And then we pass through the decoder by including the target sequence. So during training, we can use the actual target sequence. This is teacher forcing. I'm going to show this in more detail. During prediction, we can input what has been generated so far. The input of the encoder, a flag to specify if we're training or not. This is used for the dropout layers, especially because dropout layers need to function differently when you're training and not. When you're training, they randomly switch off some neurons. When you're in inference, not training, they need to rescale the output so that on average is the same as it was during dropout. And so we use this, we get the final output, the final dense layer there, and we return the output and the dictionary of all the attention weights in the decoder, if we need to visualize this later. Okay, so now for training, we're going to first create a scheduler to adjust the training rate and reduce it as we are training. So basically what you can do is you can create a custom scheduler from the learning rate schedule in the base class in Keras, and you need to define the initialization, so the constructor for the object, and this special call method to use this as an executable that will return the training rate. And here you can use whatever schedule you want. So basically this receives the step. Each time the optimizer is going to do to change the weights, it increments the step and can call this scheduler. So we can consider these, for example, this base rate, which would be the 1 over the square root of the step, or we can also take this parameter of warm-up steps, the number of steps that we have in the beginning before starting to decrease the training rate, and we use the minimum of the two to to output the learning rate here. This is just a particular formula. You can see in the tutorial the shape of the learning rate that you get here, but you can in theory use whatever you want. And the idea is generally to start with a larger training rate and then gradually reduce the training rate as we keep training the model. So the way you can do this is to include this in the optimizer. So here in the optimizer, instead of giving a fixed number for the learning rate, I give the object of this this custom scheduler that I created. So now at each time Adam will change the parameters, it will call this object, it will execute this object to obtain the learning rate for that particular update. So typically this will be done one time per batch during training. So now we're going to create these loss functions for measuring the loss and the accuracy, because we need to take into account that parts of our vectors have to be masked. So we are not going to compute the loss function over the whole sentence or the whole maximum sentence that we could have, since a real sentence will only occupy parts of it, and the same thing for the different masks. So we are going to use this mask here by discarding everything that is 0 on our sentence. We are going to compute the loss, but then we're going to ignore these parts that are outside the mask and compute the loss only for the elements inside the mask. So those that are real, those that are not masked. And the loss object here is the loss function that we're going to use. This is the sparse categorical cross entropy. And you already used categorical cross entropy. This is when we use the one-hot encoding, for example. The sparse categorical cross entropy can be used when we have those integer labels for the different categories. So this is what we're going to use in this case, because we have the identifiers of the different tokens. And the reason for creating this outside the functions, both the loss object and these running means objects that we're going to use to average the training loss and the accuracy during the epochs, is because we are going to compile the graph for all our computations and then execute it after compilation. And this optimizes training, but it requires some care that we do not create new tensors inside the computation graph. Otherwise, TensorFlow will have to recompile everything again, and we may get some serious problems, or even give us an error in execution. So this is what we're going to do in the training step, but this is just to create the model. So we're going to stack 4 layers of the encoder and decoder blocks. This is a lot less than what the original paper recommends, but this will be just a smaller version, so it doesn't take too long to train. This is the depth of the model for most representations. So we're going to use 128 vectors for each word in the embedding and in the attention layers and so on. This is the expansion we do in that stack of feed-forward layers. So you remember the one that has the first a dense layer with a rectified linear unit, and then a linear projection to the original depth. So we do expansion to 512 and then back to 128. This is the number of heads for the multi-head attention, the dropout rate, and now we create our custom scheduler, the optimizer, and we create the transformer. So now we are going to also use checkpoints during training. This is useful if you want to save your model regularly and automatically resume training, load the model, so you can use this checkpoint from TensorFlow. You specify the path and in the checkpoint manager, and you can specify with how many to keep, and it will keep track of how many checkpoints you want to keep and delete the other ones and so on. We need also to create the masks, so you need to create the padding masks for the input into the encoder and the decoder. We need to create those look-ahead masks when we are generating the sequence. We don't want the decoder to look at the next token that will come up. But basically this is just an utility function to combine these masks. And now we are going to create the function for the training step. Now here, this is something different from what we did before. We used the eager execution of TensorFlow so far, and we created the training step function that basically does this with the gradient tape. It computes the loss, and then it updates the parameters by using the optimizer, applying the gradients and so on. So this part is what we've been doing so far. The difference is this decorator here. So this TF function will trace all the computations called by this function and compile the graph. We used this briefly when we wanted to output the computation graph in one simple example in the beginning of the semester, but now we are using this for real, and we need to be careful that in this case, when we are creating this graph, this will be a statical graph, so the tensors cannot change. We cannot create new tensors during the execution and so on. And we also need to be careful, because if the size of the tensors is not exactly the same, then TensorFlow will create a whole new graph when the sizes are different. To prevent that, we can specify this signature. So we can tell TensorFlow that this would be the signature for the inputs. And as long as they have this signature, they have these 2 dimensions, so the batch and the sentence, and they are integers. These are the tokens that we have in the input and the target sentences. We can work with the same graph. This is important because when you have a data set and you split it into batches, typically the last batch will not have the same size as the others, because you're using the leftover examples and they not be divisible by the batch size. So if that happens, then if we don't warn the TF function that we can work with these signatures for the tensors, it would generate a new graph for the last batch, and we don't want that. Other things that we need to do is that these loss, the running means for the loss in the epoch, are those that we created here. The loss object also was created here. It's a global object. All of these tensors and operations in the model also have been created once in the model, so that when TensorFlow traces all the computations here, it doesn't find that tensors are being created locally and discarded, so because that would not allow it to create this statical graph. The advantage of creating this graph and going through all this trouble is that then it's much faster to train, because it's no longer Python. It's a graph created specially to put, for example, in the GPU, to spread out through the CPUs and so on. And TensorFlow can now optimize that for execution. Okay, so now we have the training loop. One particular detail is this part here. So we have an input sentence that is in Portuguese. We have a target sentence that is in English. So what we're going to input into the decoder is the target sentence all the way to the last token. So the last token will probably be empty, because this is the maximum size of the sentence, but or it will be just the end token indicating the end of the sentence. And for the target that we want outside of the decoder, we're going to shift this. So basically, we want the encoder to predict the next token given the previous tokens as the input, and we are actually going to feed into the encoder, the transformer, this target as input. So when we are using the transformer to generate new sentences, we will first, in the first iteration, feed into the decoder just the start token and obtain the first word in the sentence. And then we're going to feed there the predicted first word for it to predict the second word and so forth. But in training, we can do teacher forcing, like we saw with the recurrent networks. Instead of feeding into the decoder the predictions from the previous iterations, we are going to feed it the true previous tokens. So pretend that so far the decoder has gotten everything right, and it just needs to predict the next sentence from the previous ones that are corrected. So we're going to feed into the decoder these inputs, and then measure the loss function to the real target, which are the next tokens and the predictions. So basically, we are feeding the previous tokens in the target sentence and want the decoder to predict the next token. So this is the training part for the loss function. We will apply the gradients using the optimizer that's using our scheduler, and then keep the running average of the training loss and the accuracy so that we can output here in the training loop. So basically, for each epoch, we're going to reset the training and accuracy losses. These are running averages, so during the epoch, they will keep the average loss over all the batches, but then between epochs we reset it and start again. And for each batch we're going to train, and every 50 batches we output the accuracy and loss so far. Every 5 epochs we save the checkpoint so that if something happens we can continue from there, and so on. So after training, we can now use the model to generate data. By the way, this can take a bit to train. Depends on your hardware, but it can take maybe half an hour or a few hours, so on. So if you want to try this and you don't have a very good computer, maybe you could try it Colab. There it should run faster. And now what we can do is to use the model to generate a new sentence. So we input a sentence in Portuguese, we convert this with the tokenizer to get a tensor with the integers for the identifiers of all the words. We create we tokenize an empty sentence just to get the start and end tokens for the English tokenizer. And we are going to iterate through using our transformer by inputting the input sentence encoded, the output so far. So the output that we have so far is everything the transformer already produced, which initially it's just the start token, but then we will concatenate the predictions of the next word, and the masks, the padding masks, and so on, as we have created so far. So this means that we're going to iteratively use the transformer to output the prediction for the next word that we're going to find with the argmax from the output of the encoder. And if the predicted next token is end, the end token, we break this loop. Otherwise, we continue. And then we detokenize and look up to obtain convert from the vector of integers that the transformer is creating into a sentence in strings and return that text. Okay, so this is how we can see. To translate a sentence, we call the evaluate on the sentence. We only care about the translated text. So this is a more generic function that returns the attention weights, the tokens and the text, and so on. But we only want the text, and we convert that into NumPy, decode to UTF because this is in byte strings, and print the output. So you can see that if the sentences are straightforward, for example, este é problema que temos que resolver, this is a problem we have to solve. So the transformer works pretty well on these straightforward sentences. Este modelo parece funcionar bem. This model seems to work well, so the translation is fine. Of course, when we come to idiomatic expressions, for example, quem tudo quer tudo perde, who always wants everything to lose, this seems a bit close, but it's strange. Estás aqui, estás a levar, these are actually taking over here, so this is not even close. And estou feito ao bife, I'm done by the different tree. I don't know why this translation appeared like this, but the interesting thing here is that, of course, idiomatic expressions are very hard to translate. This would be the hardest examples, but it's easy to note that with straightforward sentences, it seems that the transformer is just translating word by word, which would not be a very good method for translating. But when we use these more stranger sentences, we see that it's not trying to translate word by word, but trying to find some pattern there in the sentence that may lead it completely astray in this example, but it shows that it's not doing a naive translation, just translating each word. Okay, so this took a bit longer than it should have, but to sum up, we saw briefly an idea of attention mechanisms and these transformer networks. So the big advantage here is that using attention mechanisms, we can deal with sequences and transform sequences without using recurrency. And this means we can use much more complex models and train them much more efficiently. We saw how to implement a transformer and lots of more advanced options and tools in Keras and TensorFlow. You do not need to learn this for grading in this course, but this is things that if you want to go forward in this in deep learning, and if you want to experiment with more complex things, then it's a good idea to take a look at these different options because they can save you a lot of time. Using dataset classes, using schedulers, checkpoints, creating layers for more complex models, and computing the graph for execution, this can help a lot with performance. So optionally, if you want, read the paper on the transformer. So this explains in detail this transformer architecture, this particular attention mechanism, and so on. And it's an interesting paper for these transformers. And this is really the state of the art nowadays for natural language processing. So we are not going to cover more of natural language processing in this course. It's just this lecture, but if you're interested in this subject, then studying transformers will be a good idea. Okay, so I'm going to log into Zoom and we can talk a bit there. See you soon.